Two, this is projectile motion. So the purpose of this lab was to observe an object with both x and y vectors and to show how the force of drag affects an object. And the result we get is that drag more accurately predicts projectile motion in real life. And so the models and principles we use are the tracker model and Glow-Script computational model, as well as Newton's first law, Newton's second law, the momentum principle, and the concept of drag. And so assumptions we make here are the object is a point mass system, and the initial velocity is average velocity for first time interval, and accounting for drag will make the model more accurate is our assumption here. And so the equations we use are F net over mass equals acceleration, and V velocity final equals velocity initial plus acceleration times time, and then our force of gravity vector is 0 and negative mg 0, and then our force of drag equals negative b v hat speed squared. And so our initial conditions here are that the camera remains stationary, keeping same frame of reference, and the eraser was given a force to begin its motion. However, position is not recorded until after the applied force has ended. And the meter stick in background is for calibration, and our eraser only moved vertically and horizontally, not in the z direction. And then our coefficient for drag is 0.0288. So our experiment description: the eraser is our system, and it was given an initial velocity. The air and earth are its surroundings. The motion was recorded to give 2 dimensions. Then using the tracker app, the position of the eraser was recorded in 1/60th second time intervals for the length of the video. And we see the effects of air resistance and drag on a projectile. And so it follows this path and comes down. And so our Glow-Script code followed this computation using the same initial velocity and initial position, and we update our velocity and position using those equations, and then F drag and F net because we have non-constant forces. And so we increment time by 1/60th of a second until 43 over 60 seconds. One model is going to use drag and one uses and gravity, and the other just uses gravity. And here is the code here, and if you run it, you'll be able to see the different arrows. You can see our velocity arrow and our 2 force arrows, that one being gravity, that one being drag, and they follow these movements. And so that will give you this data set, including the tracker data set here. And so when using that, the model accounting for drag is more accurate than the one only with gravity, and the b value of 0.0288 was found experimentally by testing which model best fits the tracker video. So our yellow line is no drag, and that's computed. So that's what happened in ideal kinematics. And then our blue line is our tracker video, so that is real life. And then we tried to match up the red as best as possible. And there are some discrepancies, but it's definitely more accurate than the yellow. And these discrepancies come from there being different like initial velocities within the equation. Like it's not the most accurate, especially because of the object that we used. As you can see here, we used an eraser which was spinning on an axis, so it rotated, and drag is going to affect it in different ways. And so the tracker and gravity models are different, and tracker and gravity only models are different. Therefore, there must be another force, and this force is drag, and when included, the model is much more accurate. Both models use velocity and position update formulas to account for non-constant forces, and our B value was the most accurate. So some errors: of course, the eraser is not point mass or spherical, so drag affects it based on its current rotation. And it's difficult to track the eraser as it rotated because it's hard to keep a central point. And then the parallax error, because we're not exactly lined up with the table and the meter stick is somewhat behind the object, so it's not in the same plane of motion, could affect how we represent a meter. Our results were that the eraser did not experience terminal velocity, as the y velocity wasn't ever constant, but our F net did change for the tracker and drag model because we have a non-constant force, and therefore gravity wasn't the only thing affecting it, and therefore drag should be considered when predicting and examining an object's trajectory. And what this means is that none of my graphs showed terminal velocity, and to find it, you could just drop the object from a very large height and that would help it have force of drag equal force of gravity at some point as it got closer to the ground. And then the time for an object thrown straight up with the same speed would be longer, because how the force of drag is determined in comparison to v equals v cosine theta, v sine theta. And so with our y component, it would be straight up, giving it the largest vertical component, and you'd have more x component velocity on the angled throw, meaning you would have more drag over that period of time because you're just looking at speed. And when you throw it straight up, you're going to go higher, which means it's going to be longer to come back to the ground. Thank you.